Hi everyone, welcome back. I'm Mr. Peck here. Now let us study a new topic called the thermodynamics. So what is actually thermodynamics? Okay, let us look at the slide. What is actually thermodynamics? Thermodynamics is the study of how energy can be transferred between a gas system and its surroundings. So we have two objects in concern. Okay, first of all is the gas system. The second one is called the surroundings. So the two most important objects in this chapter is the gas system and the surrounding. And thermodynamics is the study of how energy is transferred between these two objects in concern, which is the gas system and surrounding. How the energy is transferred between the gas system and also the surroundings. So thermodynamics concerns only about energy. Yeah, it's all about energy. It's all about energy. So first of all, what is actually gas systems and the surroundings? Okay, let me take one example. The piston cylinder inside the car, which is this one. Okay, this is the piston cylinder that can be found inside the car. Okay, this is the piston and this is the container. Okay, this is the container. And inside the piston cylinder, we have the gas or the fuel. Okay, the gas or the fuel itself is called the system. This is very important. The gas is the system. Okay, and then what is surrounding? Surrounding is the piston itself. The piston, the container, and even the surrounding itself is called the surrounding. The piston, the surrounding, they are called the surrounding. Okay, the gas itself is called the system. The gas is called the system. So thermodynamics is about what? It's about how energy can be transferred between these two objects. Yeah, how energy can be transferred between the gas and the surroundings. That means how the energy transferred between the gas and surroundings. For example, let me take one example. Yeah, that means, for example, heat maybe can be absorbed into the system. Yeah, the heat from the surroundings, the heat energy from the surroundings, maybe can enter from the surrounding into the gas. So this heat is the energy. Yeah, it transferred from the surrounding into the gas. Now inside the gas, it has the internal energy. Okay, internal energy. The gas also will use its own internal energy to push the piston up. The piston is the surrounding. Yeah, is part of the surrounding also. So gas also use its own energy to push the piston up. So the gas also do some work. So energy is transferred from the gas to the piston, which is the surrounding. So do you see that? How the energy transferred? Energy is transferred in the form of heat, and energy also transferred in the form of work done. Yeah, from the surrounding go into the gas is the heat energy. From the gas go to the piston or the surrounding. Yeah, the gas goes into the energy transferred from the gas to the piston in the form of work done. Yeah, even the energy also can be transferred out from the gas to the surrounding in the form of heat. That is called the heat loss. That is called the heat loss. Yeah, maybe heat. Yeah, in the form of heat, energy maybe can be lost. So this describes how the energy transferred between the gas system and the surroundings. So this is thermodynamics. Right? So I will elaborate more on this energy transfer, yeah, which is inside this chapter. Okay, now effect of such energy transfer is the change in internal energy of the system. So when there is energy of such energy transferred, it will change the internal energy of the system. So for example, like just now I said, the heat energy from the surroundings goes into the gas. So this internal energy of the gas will increase. We learned about internal energy before, isn't it? Internal energy is the total kinetic energy of the gas. Total kinetic energy of the gas. In the previous chapter, we learned about internal energy. Internal energy is the total kinetic energy of gas. So just now, the gas is called the system. So the gas itself, it has internal energy. So if the heat energy transferred from the surrounding into the system, the internal energy of the gas will increase. Or if the heat energy transferred from the gas to the surrounding, if heat loss, so the internal energy of the gas will decrease. So it will affect the internal energy of the gas when there is such energy transfer between the surrounding and the gas. Like this one, heat absorbed, and this one is the heat loss. So this heat absorbed and heat loss, it will affect the amount of internal energy inside the gas. Okay? So besides, this will also affect the macroscopic properties of the system like pressure, volume, and temperature. So why it affect all these properties? Because about the system. What is the system? Is the gas, isn't it? The system is the gas, and the system or the gas, it has the internal energy, which is also the total kinetic energy of gas. So do you still remember the formula for internal energy? The internal energy of the gas, the internal energy of the gas is what's the formula? F over 2 NKT, isn't it? So just now I already explained the energy transfer will change the internal energy of the gas. So when the internal energy of the gas is changed, so the temperature of the gas will also change. It will change the temperature of the gas. So when the temperature of the gas is changed, so the following formula, which is the we call the PV equal to nRT. You see that? When there is energy transfer, okay, when there is energy transfer, so it will change the internal energy of the gas or the total kinetic energy of the gas. So when the internal energy is changed, it will change the temperature of the gas. When it changes the temperature of the gas, again, when there is energy transfer, it will change the internal energy of gas. When it changes the internal energy of gas, it will change the temperature of the gas. When temperature is changed, the volume will change, the pressure will also change. So it will affect the macroscopic properties of the system like pressure, volume, and temperature based on the formula PV equal to nRT. Then there comes all the laws. Remember, we have all the laws. For example, we have Boyle's laws. We have Boyle's law. We have Charles' law. We have the pressure law. All these come into effect. Yeah, all these come into effect because of PV equal to nRT. Okay, PV equal to nRT. Yeah, because of the changes of pressure, volume, and temperature. Okay, that's about the thermodynamics. So now, let us look at the first law of thermodynamics. What is actually first law of thermodynamics? First law of thermodynamics is this formula. Okay, Q is the heat. Yeah, the heat equal to the change in internal energy plus work done. What is this? What is Q? Heat. This is called the heat. This is the delta U is the change of internal energy. and W is the work done. For example, I give one example. Heat is absorbed into the gas. When the heat absorbed into the gas, so what happened to this energy transferred into the gas? It will cause an increase in internal energy of the gas. Because heat has gone into the gas, the energy has entered the gas. So the internal energy of the gas, of course, will increase. And sometimes the gas also will use its own energy to do some work. For example, like pushing the piston up. So the gas also do some work done by the gas. Okay? So this is what it means by this first law of thermodynamics formula. This is all about conservation of energy. No energy is lost. Yeah, no energy is lost because like for example, that when the heat from the surrounding, the heat energy transferred from the surrounding into the gas. Yeah, when it goes into the gas, this heat energy will not be lost. Yeah, it will store inside the gas in the form of internal energy. And after that, the gas also use up its own internal energy to push up the piston. So this is called work done by the gas. The gas do some work. Okay. So this is called work. This all is conservation of energy. No energy is lost. Okay. Yeah, you cannot say the heat energy from the surrounding enter the gas, and then this heat energy just disappear. Yeah, just disappear. It won't disappear. This heat energy enter the gas. It will be stored in the form of internal energy of the gas. Okay. So no energy is lost. Okay. Yeah, that's why we call this formula. This formula is related to conservation of energy. Okay, it's related to conservation of energy. Now, in this chapter, we have one very important graph, yeah, that we need to understand. Okay, which is this PV graph, pressure volume graph. Okay, this one, pressure versus volume graph. Okay, as usual, the all must be in SI unit. The pressure must be in Pascal. Volume must be in meter cube. All must be in SI unit. Pascal, meter cube. You cannot leave at other unit. Okay? Pascal and meter cube. All must be in SI unit. So, why this pressure volume graph is so important? Why is it so important? Because in the Boyle's law, Charles law, pressure law, we always use this graph, isn't it? Pressure volume graph. And just now I did say that the energy transfer will cause a change in the internal energy. Will also cause a change in the temperature of the gas. When the temperature is changed, it will affect the pressure and volume of the gas. So this thermodynamics will study the changes of pressure volume graph. Yeah, we'll study the changes in the pressure volume graph. Yeah, because the Boyle's law, Charles law, and pressure law have come into effect. Have come into effect in this chapter. Okay, first of all, we have the y-axis is always the pressure, the x-axis is always the volume, and yeah, we have pressure and volume. So how about temperature? How about temperature? We don't have axis for temperature. So you see, you can see here are dotted lines, isn't it? These dotted lines, they are called isothermal lines. Isothermal lines. That means, as you can see, these isothermal lines, as you go further and further away from the x and y axis, when you go further and further away from the axis, the temperature will increase from 300 Kelvin. This is just examples of temperature. Yeah, it can be other values. Yeah, it can be other values. I just take examples of temperature. So the curve which is nearer to the axis is always the lower temperature. The curve which is further away from the axis is always the highest temperature. So when the curve going further and further away from the axis, the temperature also increase. So okay, what exactly is this isothermal lines? Isotherms line. Iso means same. Let me write something here. What is mean by iso? Iso means same. What is means by therm? Therm is the thermometer, isn't it? I talk about thermometer. What thermometer measure about? Temperature, isn't it? Thermometer measure temperature. So isotherm means same temperature. Same temperature. What is it mean by same temperature? That means along the dotted line, on the same dotted line, all the points on the same dotted lines, all the points on the same isotherm lines, they have the same temperature. That means, for example, if I take this point here, point A, and point B, and point C, point A, B, C have the same temperature of 500 Kelvin. 500 Kelvin. Let me take the point, let's take this D. This is the E, and this is the F. This point D, E, and F all have the same temperatures of 300 Kelvin. Okay? D, E, F, all these points have the same temperature of 300 Kelvin. Point A, B, C, all these points have the same temperature of 500 Kelvin. And the middle one, all the points on the middle line has the same temperature of 400 Kelvin. Okay? So, this is called isothermal lines. Same temperature lines. Okay. This is very important. Along the x-axis, when to the right, we can say direction to the right, the volume increase. As usual, like the axis. Going to the right, the volume increase. That means, if we go to the right, the volume increase, or we can say the gas expansion. Going to the right, expansion, volume increase. If going to the left, is compressed. Yeah. If going to the left, volume decrease. Volume decrease or compression. Well, maybe I can write like that. If going to the left, is volume decrease, or we call it compression. Compression. Okay. Now, going upward. Going upward is pressure increase. Pressure increase. Going downward, pressure decrease. Okay. Going upward, pressure increase. Then how about temperature? Temperature is going away from axis. Going away from pressure volume axis, the temperature increase. Okay. So going to the right, volume increase, expansion. Going upward, pressure increase. Going away from axis, going away from axis, temperature increase. Temperature increase. Okay, or getting hotter. Getting hotter. If going towards the axis, if you're going towards the axis, going towards the pressure volume, axis, it getting colder. Temperature decrease. Getting colder. Okay, going away from the axis, getting hotter. Temperature increase. Okay, now that's about the pressure volume graph. Later we will study more on pressure volume graph. Now this one also concerns about the pressure volume graph, but this one is about the area under the graph. What is it mean by area under pressure volume graph? In short, the area under the pressure volume graph is called the work done. Work done. Yeah, it measures the work done. Work done is the area under the process curve. Or we have one formula. Work done. How to calculate the work done by the gas? it is integration of pressure versus volume. Integrate pressure, yeah, maybe from volume 1 to volume 2. So when talk about integration, integration is about the area to get the area under the curve. Okay, so work done is actually integration of pressure versus volume. So integration means area under the graph. So area under the graph it measures about the work done of the gas. Okay, these are some important concepts I need you to first understand before you going into the chapters. Okay, so stay tuned for the second part of the videos. Thank you. Bye.